question 3 from the worksheet for Unit 4, and the first question reads, simple harmonic motion. In terms of the acceleration, state 2 conditions necessary for a system to perform simple harmonic motion. So for that, we know we are looking at our formula here. A is equal to minus omega squared x. That is our defining equation. So it's the two things. It's the minus and it's proportional to the x. So we have that our acceleration is proportional to the displacement, the x from the equilibrium. And also we have the negative sign over here, so the A is always directed towards the equilibrium, or in the opposite direction to the displacement, so the equilibrium. Please excuse my writing there. Fine, so that's your basic definitions there. So for B, a tuning fork is sounded, and it is assumed that each tip vibrates with simple harmonic motion. And here we've got this situation over here that full to and fro is D. So from the top position to the bottom position we have D there. The extreme positions of the oscillating tip are separated by a distance D, just as what I said. In terms of D, the amplitude of the vibration, so that's full. Amplitude is always from the equilibrium, so that would be from the middle upwards, so it would be D over 2. Now, it then asks on the axis below, we need to sketch the graph for this. So just going down there, just pulling this up, we need to sketch the graph of displacement against time. Now if I look at my formulas here, I'm going to be using either one of these two, because here's I've got my displacement, my x, and my time. I could use the cosine or the sine, so it's basically a sine graph or cosine graph. Now I hope you will draw yours better than I will, because I'm not very good at sketching with this pad here. Actually, let me start with a positive. I'll go positive graph. I'm going to use a sine graph, and I'll go positive and I'll go negative there. So we're going to get something like this. As you can see, it's not great. It needs to look like a sine graph. Mine isn't wonderful at all. You also need to look better than that. And this will continue on like that. So that's your displacement. This obviously over here, now this actually comes up in the next question here. This is obviously D over 2, that over there. It says on your graph, label the time, the period T, and the amplitude A. So the time T is after one full period, so it's there, we'd have T there, and at the full amplitude there we would have our A. So you would label it like that. Fine, let's go on to the next part of the question now. So we go down here, and we've got this over here. So it's question C. The frequency of the oscillating tip is 440 Hertz. So that's the frequency, 400, the frequency of the oscillating tip. And the amplitude, that will be x0, is 1.2 millimeters. This highlighter is knocking out everything, but I hope you can still see it there. So we are being asked to calculate firstly our linear speed of the tip and the acceleration, and always to see here it says determine the maximum linear speed. So which formula are we going to use? Well, we'll use this formula here for the velocity. And then we'll use our defining equation. A is equal to minus omega squared x. We're going to use this formula also because we need our omega, and we know that that's equal to 2 pi f, because our frequency is equal to 1 over our period, and we are given our frequency in this case. So the linear speed, we're going to use this one over here, but because it's the maximum speed, this x0 here is actually 0, because the the maximum speed occurs at the equilibrium position. So we're going to get v is equal to, now we don't need to be more about the plus minus because we're dealing with speed, so we're not worried about a vector, but that omega is going to be 2 pi f, and it's going to be multiplied by the square root of x0 squared. This cancels out to be 0, so you've just got that, and those square roots cancel out, so just by x0 there. Now you can, if you want, but they haven't asked you to, you can convert this millimeters into meters. I'm just going to leave it as millimeters, but make sure that, so it's, sorry, let me not do it there first. I'm first going to do the 2 pi, so let's just take it out there, is equal to 2 pi 440 times by our x0, which is 1.2, times by that, and that will give us our result, and it works out to be 3.3 meters per second. So if I converted that millimeters into meters, I'll get that. Obviously that's going to be 3,300 millimeters per second, like that, if I was doing it in millimeters. The acceleration, the same thing. Acceleration is equal to minus omega squared x. Because we're looking at our maximum, that occurs when our x is equal to x0 at our maximum, so it's going to be again similar situation. But now we've got this omega squared. Now we can keep our negative sign, and then we always know that's just saying that it's in the opposite direction to our displacement. But this is going to be 2 pi 440, and we're going to need to square that whole thing there, times 1.2. So what should we do? Should we put it into meters? Let's do that. 1.2 times 10 to the negative 3 meters, and that will give us our a final answer there, and it works out to be about 9.2 times 10 to the 3 meters per second to the negative 2. Now notice here two significant figures, because I've got two significant figures in my data, so you've got to round it to two significant figures. If you don't, you're going to lose -1 mark for significant digits there. Right, so make sure that that is correct. Okay, thank you.